Assalamualaikum warahmatullahi wabarakatuh. Good evening to my lecturer and peers. We are from Group Patron and we are here to present our project well completion. So the first part is well data. We obtain our well data from our lecturer. So these are the well objectives. The type of well is producer. Our flow target is oil, and the horizontal distance is 801 meter. So we are given the reservoir data and flow properties, and we found out that our well is Mike Isabel, and we are given the simulated well logs and the pressure window. Firstly, this is the casing setting part. So from the well data that we obtain, uh, we able to determine the type of casing that we need to use. So from the calculation, we determine that the PSI for diffusion stick limit doesn't bypass 2200, so we do not need intermediate. So this is the type of casing that we pick at the table, and this is the grade that we pick.
Next, for the conductor casing burst and collapse design at 800 feet, we are using H40 grade as shown on the graphs with a 1.1 safety factor. Our maximum design loss fell well below the H40 capacity limits of 1530 psi for burst and 520 psi for collapse. So this is very secure. We applied a similar approach to the surface casing down to 9,350 feet, selecting the 13.38-inch S95 casing. This graph clearly shows that our entire burst and collapse design loss profiles remain far below the S95 maximum limits of 7,770 psi and 6,240 psi, but integrity for both sections are fully guaranteed.
So moving on to the calculation of casing setting. Uh, First things to note, the conductor casing is set at a depth of 800 feet, while as for surface casing, it is set at depth of 9,350 feet. Uh, for production casing, we have to calculate the kickoff point at 9,850 feet first. So from there, the length of the weighted point is around 3,838.5 feet. So production casing is set at 13,188.5 feet. So moving on to the cementing program. So firstly is the slurry design. Our well use the two slurry system lead until to balance formation protection with high strength at the bottom where the horizon located. So for lead slurry, it is used for the conductor casing and the upper section of the deeper casing strings because the shallow formation weak. So we only need to provide lighter weight slurry that still provide a reliable seal. As for tail slurry, it is placed at the bottom of the section of the well, covering the casing shoe, pad hole, and the target oil reservoir, because the bottom well experiences much higher temperature and pressure, and the oil zone needs to be isolated safely. So moving on to the placement technique, uh, we use the conventional subsurface displacement method using a lead and tail sequence. So these are the step-by-step placement. First, we pump the lead, followed up by pumping the tail slurry behind it, and we launch the rubber behind the tracery, and the series are pushed out of the bottom of the casing shoe and pushed outward into the anal space. And lastly, the pumping stops when the high center cement settled at the bottom, and the light cement fills the upper section at its planned height. So we continue to the last part, which is volume calculation. So for volume calculation, we follow step by step to like casing in hole, and then we accumulate we account the rat hole and the shoe track, and we calculate the total volume or the whole total volume from from bottom of the rat hole until conductor casing. Yeah. And we calculate the slurry density, the yield of slurry, the sex, and the amount of water. So continuing to our to the conduction casing. So since it start at the deviated point from the kickoff point, the calculation slightly differ, but it still follow the same step, which is total volume, uh, to account for the total volume, the slurry, the yield slurry, the amount of sacks, and the amount the amount of water used. So to point out the value of X, it amounts to the lid of slurry sitting inside the slanted section, and the value of 1376.4 means the remaining open hole for trail slurry to occupy. So that's all for me.
Okay, based on our criteria, we evaluated four tubing size, and our primary focus is to ensure efficient flow without exceeding erosional velocity limits. At our standard flow rate of 800 BOPD, the 3.5-inch tubing yields a flow velocity of 1.07 feet per second, and when compared to the Baxandrel erosional velocity limit of 2 to 3 feet per second, this gives us a safety margin of 0.43, which is well below the risk threshold. And why did we not choose the 278-inch tubing? Well, it is acceptable, but it becomes higher risk at our peak capacity of 1,200 BOPD. So where the velocity reached 2.4 feet per second, it almost hitting the erosional limit. So we choose 3.5-inch tubing to maintain the long-term integrity and to it's and to mitigate the sand risk in our deviated well. Okay, moving on to the material selection, this decision is driven by the well's corrosive environment, specifically CO2 and H2S levels. And our data here shows a CO2 partial pressure of 3.53 atm, and it can causing sweet corrosion. And it significantly exceeds the standard 13 CR tolerance of about 1 atm at high temperatures. Additionally, our BHT 135 Celsius exceeds the 30 CR temperature limit of 50 Celsius. Looking at the justification chart here, our specification well conditioned placed us squarely in the super 13 CR zone. So we decided against upgrading to higher corrosion resistant alloys because our H2S pressure is still relatively low, which is 0.00655 atm. So using a higher grade material will not be economical or offers no significant technical advantage. Finally, let's look at our pecker configuration. We set the permanent hydraulic pecker at 3,200 meters TBD, which is 227 meters above the perforation. This spacing accommodates blast joints and logging, stabilize the pressure gradient, and it also allows safely for walkover kill fluids. With 10,000 psi against 2,708 psi differential pressure, we maintain a solid safety factor of 3.69. And then here, for the elastomer seals, we choose HNBR. Why? Because NBR fails our 135 Celsius well temperature, and then here, EPDM lacks of H2S resistance, and AFLAS is simply because it is not economical. So HNBR is perfectly balanced thermal durability, H2S and CO2 resistance, and it is cost efficiency.
So next, I would like to share on our perforation strategies on this well. So before we make our decision, we first study the well context first. So this well is an oil producing well, and it has a net pay of 35 meters. And the lithology for this well is a consolidated sandstone, and it has a BHT of 135 degrees Celsius, which means it is a high temperature well, and it has a 13 ppm of H2S and 0.70% of CO2, which means it is a corrosive well. So for our depth selections, we interpret it through the logging data. So from what we have learned through our formation evaluation class, when the gamma ray value is low and the resistivity value is high, it means that it's a oil bearing zone, which means that we will perforate that zone. And when the gamma ray value is high and the resistivity is low, it may not be a potential hydrocarbon zone, so we will not perforate that zone. So from our logging data that is given for this well, we will choose to perforate 3,435 to 3,450 meters as our pay zone, and we also perforate 3,456 to 3,472 meters as our main pay zone because it shows a higher resistivity and a lower porosity, which means that it may be a more potential hydrocarbon zone. For the perforation method, we are going to use ITCP. We use ITCP because this well is a high temperature well and it's a deep well. For ITCP, it is suitable for deep well and high temperature well. So we believe that ITCP is really suitable for this well. And also for the perforators, we will use sharp charge perforators because sharp charge perforators is suitable for high temperature and deep well. Yeah. And it has a high explosive which can maximize our production. So next, about the shot density and phasing. For the upper pay, we are going to use a shot density for around 8 to 10 SPF. But for the main pay, we are going to use 12 SPF. It's because for the main pay, it has a higher potential that it will contain more hydrocarbons. So we will use more shot density at that area. And for the upper pay, we will use a lower, which is 8 to 10 SPF to save our costs, but at the same time still maintain the productivity. Yeah, so for the phasing, we'll use 60-degree phasing because it can distribute shots around the casing and improve circumferential inflow. So for the pressure recombination, we'll use slightly underbalance. Why we not use overbalance? Because overbalance will damage our formation and reduce oil flow after perforation. So we don't want this to happen, so we will not use overbalance. But why we use slightly underbalance but not strong underbalance is because this well has a moderate sanding risk, and so if there's an excessive drawdown, it can damage our productivity. So we will not use strong underbalance. So yeah, slightly underbalance is our choice. And for the perforation fluid, we are going to use corrosion inhibited fluid because this well is a corrosive well. It has H2S and CO2 exposure. So with corrosion inhibited, like such as CaCl2 and CaBr2, it will be a really suitable perforation fluid for our well. This is our final perforation strategy summary for our well.
Good day everyone. So my presentation is about the selected downhole tools for our well completion design. I will explain each selected tools and why it is suitable for this well. So the proposed design is a single tubing completion using 3.5 inch production tubing, a hydraulic set production packer and a downhole safety valve system, circulation equipment, landing nipples and also a mule shoe guide. So this design is selected because the well has a long horizontal displacement, high temperature and also mildly sour produced fluid. Therefore, the completion must provide safe production, reliable flow control and also convenient access for future intervention. The first selected tool is the double pin sub. It is installed at the top of the completion string to connect the uppermost tubing joint to the tubing hanger. It must have the same grade diameter, drift diameter and thread type as the production tubing. The main flow conduit is a 3.5 inch production tubing string. This size is provisionally preferred because it is larger internal diameter, provide better flow capacity and easier through tubing access compared with smaller tubing. The premium gas tight connection are also recommended because the produced fluid contain hydrogen sulfide and also carbon dioxide. Pump joints are included to provide accurate space out. They allow important equipment such as the safety valve, sliding side door and production packer to be positioned at the required depth. Heavy wall flow couplings are installed above and below the TRSV and other significant restriction. This coupling protect the ordinary tubing from erosion caused by turbulence and high velocity flow. The tubing retrievable safety valve or TRSV is selected as the primary downhole emergency shut-in barrier. It is operated from the surface through a hydraulic control line and can automatically close the well during an emergency. A ball and seat closure is preferred because it is compact and can help clean deposit from the valve seat during closure. The safety valve landing nipple is also recommended as a backup safety option. If the primary TRSV develop a leak, it can be locked open and a wireline retrievable safety valve can be installed in the landing nipple using slick line. This avoids the immediate need to retrieve the entire tubing string. A selective landing nipple is installed in the upper tubing string. It allows a wireline plug or other flow control device to be set inside the tubing. This is useful for the pressure testing, temporary isolation and minor work on the wellhead or Christmas tree. A sliding side door is selected above the production packer. It also provides control communication between the tubing and the analyst for the completion fluid displacement, tubing cleanup, pressure equalization, well killing and future work over operation. During normal production, the sliding side door remains closed. A retrievable single hydraulic set production packer is selected as the sole production packer. It seals the tubing casing annulus and direct all the reservoir fluid into the production tubing. The hydraulic set design is particularly suitable for the deviated and horizontal well because it does not require tubing rotation and can be retrieved together with tubing. Below the packer, a no-go landing nipple is installed to provide a positive depth stop for plug and test tools. It also prevents slickline equipment from travelling below the completion string. Finally, a mule shoe guide is installed at the lower end of the completion. It protects the lower connection and provides a smooth entry that helps slickline tools re-enter the tubing. So, in conclusion, the recommended completion consists of 3.5-inch premium tubing string, a double pin sub, pop joint, a TRSV, flow coupling, a safety valve landing nipple, selective landing nipple, a sliding side door, a retrievable hydraulic set packer, no-go landing nipple, and also a mule shoe guide. This arrangement provides a safe production, operational flexibility, tubing protection, and easier future intervention, while remaining suitable for the well horizontal geometry, high temperature, and also corrosive fluid conditions.
Assalamualaikum. My name is Danial bin Muhammad Nasir, and I will be presenting about the risk mitigation part. So, in this part, I will explain about the risk mitigation for Petron well completion designs. So, based on the well data, Petron is an oil producer with consolidated sandstone, 35 meters total net pay, bottle home temperature of 135 degrees Celsius, moderate sanding risk, 30 ppm H2S and 0.7 CO2. Therefore, the main risks are sanding, formation damage, corrosions, high temperature, well control failure, annulus isolation failure, and erosions. So first, sanding risk will be reduced through selective perforation and controlled drawdown. The well will only perforate the good oil pay zones at 3435 to 3450 meters and 3456 to 3472 meters. The poor quality interval from 3451 to 3455 meters will not be perforated because it may increase sand production. So the main lower pay interval will use 12 shots per foot, while the upper pay interval will use 8 to 10 shots per foot. This will help the distribute flow and reduce velocity through each perforation tunnel. Second, the well will use slight underbalance perforation of 250 to 500 psi. This means the wellbore pressure is slightly lower than reservoir pressure during perforations. It will help clean the perforation tunnels, but it is not too high, so it reduces the chance of sanding. Third, the formation damage will be minimized by using integrated tubing conveyed perforating or ITCP with clean and filtered CaCl2 or CaBr2 completion brine. This fluid is low in solids, stable at high temperature, compatible with sandstone, and corrosion inhibited. Next, corrosion risk from H2S and CO2 will be controlled by using suitable tubing material, premium connections, corrosion resistances, and corrosion inhibitor. Since the bottom hole temperature is 135 degrees Celsius, all downhole tools such as the packer, TRSV, SSD, seals, and perforating charges must be temperature rated. So for well control, a tubing retrievable safety valve or TRSV will be installed as the main emergency shutting barrier. A safety valve landing nipple or SVLN will also be placed above it as backup if the TRSV leaks. So a single hydraulic set production packer will be used to isolate the annulus and direct production into the tubing. So in conclusion, the risk mitigation for Petron well focuses on controlling sanding, preventing formation damage, managing corrosion and high temperature, and maintaining well control. This makes the completion design safer and more reliable for production. Thank you. In summary, this project proposed a complete well completion design for the Petron oil producing well. The selected casing program used H40 conductor casing and 13.38-inch S95 surface casing, while intermediate casing is not required based on the pressure assessment. So for the production casing, 3.5-inch super 13CR tubing was selected because it provides good flow capacity, lower erosion risk, and better corrosion resistance. A hydraulic set packer with HNBR elastomers is used to provide annular isolation under high temperature and corrosive conditions. The recommended perforation intervals are 3435 to 3450 meters and 3456 to 3472 meters. ITCP with high temperature shape charges and slight underbalance is proposed to improve flow communications while reducing formation damage and sanding risk. Overall, this design supports safe production, well integrity, corrosion control, sanding mitigations, and future well intervention for the Petron well. That's all from us. Thank you.